Hello, everyone, and welcome to today's session. Today, we'll be discussing Forane 516A, which is Arkema's very low GWP replacement refrigerant for R134A. I'm Chris Crosby, Lead Technical Service Engineer for Arkema's full line of Forane refrigerants. Thanks to everyone who is joining us today. Let's get started. First, a little bit about myself. I've been working in the HVAC and refrigerant industry for over 15 years. Early in my career, I worked for a large HVAC OEM doing HVAC system simulation, design, testing, and production for about 5 years. Since then, I've been working for Arkema about 13 years, all within our fluorochemicals division. I've held positions related to refrigerant packaging, bulk transportation and deliveries, and most recently within our R&D organization, working on the application of refrigerants in HVAC and refrigeration systems. I'm an active member of ASHRAE, AHRI, and the SAE on the automotive side. So let's go over the agenda for today. We'll start out with a brief overview of Arkema as a company. From there, we'll move into the main portion of the presentation, which is discussing Arkema's Forane 516A refrigerant. We'll cover the properties of this new refrigerant, and then we'll move into discussing properties of the system drop-in test results, along with specific applications of the refrigerant in heat pumps, chillers, and then move on to discuss material compatibility testing, as well as the total equivalent warming impact calculations known as TWE. And then finally, we'll wrap up with a brief conclusion. So who is Arkema? Arkema is a global materials company based in Cologne, France, which is just outside of Paris. Arkema's activity is structured around 4 complementary business segments, all dedicated to materials. These 4 segments are adhesive solutions, advanced materials, coating solutions, and finally, intermediates. In 2021, the group as a whole reported €9.5 billion in sales globally. Our products are sold in a diverse variety of markets. These markets include areas such as general industry, paints and coatings, building and construction, food and water, electronics, and automotive and transportation industries. Finally, the company benefits from a balanced worldwide geographic presence, split fairly evenly between North America, Europe, and Asia. Of course, none of this is possible without the amazing team of people working at Arkema. Arkema is backed by 20,000 employees operating across 141 production plants and 16 R&D centers in some 55 countries across the globe. We continue to grow and hire more than 2,000 new recruits in 2021. Arkema is committed to its more than 10,000 customers, including many of the world's leading brands. As with any top company, we are committed to innovation and developing new products. In order to continue doing this, Arkema has over 1,600 researchers working in our 16 R&D centers across 3 continents. In order to design the materials of the future, Arkema relies not only on strong R&D, but also on strong partnerships, with more than 60 R&D partnerships globally. In 2021, Arkema filed more than 200 patents and invested 2.6% of our sales back into R&D. This all leads into growth in sales and development of new and sustainable products. In fact, by 2030, Arkema's goal is to generate an additional €1.5 billion in sales from our innovative new products. Arkema is a group committed to providing materials which help create a more sustainable world, with a corporate social responsibility aimed at creating value for all stakeholders. We do this by offering sustainable products driven by cutting-edge innovation, a commitment to act as a responsible manufacturer through actions for people's health and safety, as well as for the climate and the environment. And finally, by cultivating an open dialogue and close relationships with all of our stakeholders. Now that you know a little bit more about who Arkema is, let's talk about an exciting new product we've been working on, Forane 516A, which is a very low GWP 134A replacement refrigerant. So what is Forane 516A? On the right-hand side of this slide, you'll see a summary of the refrigerant. This refrigerant is made up of three components. 77.5% of the blend is R1234YF, 14% R152A, and 8.5% R134A. All three of these components are combined to create an azeotropic blend. This means that it has no fractionation and no glide. So in essence, this material, even though it's a blend, it performs very much as a single component refrigerant. It has a GWP of 142, and on the bottom right, you can see the GWP of 516A as compared to 134A, and you can see that it's a 90% reduction in GWP. It is classified as an A2L by ASHRAE, so it is mildly flammable. So it can't be retrofitted into existing products today that use an A1 refrigerant. However, it is considered a design compatible alternative to 134A, meaning that it can be used in many R134A systems that are being designed by OEMs with very little additional design modification. We have evaluated this material in-house and with our partners in R134A air-cooled screw chillers, low ambient heat pumps, and it has showed very promising results in these R134A optimized systems. And we will go over some of those in the coming slides. So when you look at the properties of several R134A alternative refrigerants as shown in the table on the slide, you can see that a couple of candidates stand out. In particular, the alternatives to 134A that stand out are R513A and R516A. R513A is very appealing in the interim midterm solution because it has a lower GWP than 134A at 631, but not a low enough GWP for a long-term solution. It is also very appealing because it does have an A1 ASHRAE safety classification, so it can be used in many R134A systems out there today as a retrofit product to be able to use a lower GWP refrigerant. It has very good properties that closely match 134A and is being used in systems today. When you look at the longer term replacement refrigerants out there that get you a much, much lower GWP, this is where R516A really stands out. It has, as I mentioned before, a 90% reduction in GWP from 134A. So you have a GWP of 142. That gets you below 150, which we believe will be low enough as a long-term solution to replace 134A. It is an A2L, so it does have a mild flammability, and that has to be taken into account in design. When you look at the remainder of the properties, it very closely matches 134A, gives you capacity and efficiency very similar to 134A, and through some of our testing, we've seen efficiencies actually improve over 134A. This is a big performance gain when compared to some of the alternatives. When you look at other products like R1234YF or R1234ZE, you can see that they take a big hit in performance when compared to 134A. 1234YF, you take a much larger hit in capacity, as well as a much larger hit in energy efficiency. And with R1234ZE, you take an extremely large hit in capacity that is very tough to overcome with your designs. On the right-hand side of the slide, you can see the vapor pressure, the temperature pressure chart comparing all of these products. And you can see that 516A and 513A are the two products that most closely match the properties of 134A. So again, this all leads to my previous statement that R134A is an ideal design compatible replacement for both heating and cooling applications where 134A has typically been used. So let's take a deeper dive into the simulated cycle performance of 516A and other alternatives. So as you can see from the first chart on this slide, R516A and R513A both show comparable COP and capacity to 134A. However, R1234YF showed a 5% drop in cycle performance. The second two charts on this slide show the compression ratios and compressor discharge temperatures of R134A, R516A, and other alternatives. As you can see from these two charts, all of the HFO options showed favorable compression ratios and compressor discharge temperatures when you compare them to the 134A baseline. This is a very promising results that can help broaden the operating map for these systems. Now let's transition into some actual system testing that we've done. First, we'll discuss refrigeration unit testing performed at Arkema's in-house controlled ambient facilities. For this testing, we selected a commercial reach-in refrigerator with top mount components, a single glass door that was factory charged with 134A. The unit that we used was commercially available and purchased new specifically for this testing. We tested the unit first with a baseline charge of 134A that it came with from the factory, and then we tested the unit with several alternative refrigerants. All of these products were drop-in tested in the system with minor adjustments to the TXV in order to maintain the proper superheat per the manufacturer's recommendations. We collected test data off of this system for 24 hours, and it was instrumented so that we could collect the compressor power, the fan power, and calculate the total energy consumption of the unit. So the first test condition that we ran this unit under was 75 degrees Fahrenheit or 24 degrees Celsius. This was the temperature in the controlled ambient facility outside of the test unit. So as you can see in the first chart, we show the performance relative to 134A. This shows the compressor total runtime as well as the compressor power consumption. As you can see, R516A had a lower compressor total runtime than the alternatives, and it had less compressor power consumption. When we look at the energy consumption relative to 134A of the three alternatives that we tested, you can see that 516A performed the best. It had approximately 4 to 5% less energy consumption than 134A and much less than R513A or R1234YF. So R516A offers excellent potential energy savings over all of the refrigerants that we tested. The second test condition that we ran the unit at was a higher ambient test condition at 90 degrees Fahrenheit or 32 degrees Celsius. We repeated the same test that we did previously using the higher ambient condition. And again, we saw relatively similar results to the previous condition. R516A consumed the least amount of energy when compared to all the alternatives and performed very similar to 134A in this unit. I will note that we did go back to R134A when completing all of these refrigerants and tests so that we could confirm that the baseline performance was still achievable with the unit after testing all of these products. And we did find that the unit did still perform the same as it did originally. So we did not see any degradation in performance in the unit as a result of any of this testing. The next application I would like to discuss is R516A and heat pumps. As everyone is probably aware, heat pumps are quickly becoming the heating method of choice in many applications across the globe. So in this application, we targeted a low ambient air-to-water heat pump with one of our partners in the industry. The unit that was used was an oil-free centrifugal compressor. That compressor allowed 30 to 50% energy reduction from conventional compressors. The results of this testing were published in a joint R516A paper presented at the 2021 Heat Pump Conference. Some of the results are shown here on the slide, but the additional details are available in that paper if anyone is interested. I wanted to touch on a few of the highlights of that. So when we compared the performance of R516A relative to 134A, we saw that it performed very similarly in both heating and cooling, in capacity, COP, as well as compressor speed. When we looked at the discharge temperatures of the product, we saw that 516A had both lower discharge temperatures in cooling and heating modes, which allows a broader compressor operation map, which is definitely a performance gain. The final application we'll discuss is chillers. R516A has been evaluated as a replacement for 134A and medium pressure screw chillers. So again, we partnered with someone else in the industry to perform this testing. And this data has also been presented at industry conferences in the past at ASHRAE. So when we look at the results, you can see that R516A performed almost identical to R134A in this application. On the left, you can see the capacity of the unit, which maintained very close capacity. And then on the right, we see the efficiency, the COP, and we can also see that it performed very similarly. So again, another application where we see that R516A performs very comparable to 134A. As with any new refrigerant, one of the steps to commercialize the product is to complete material compatibility testing. For this, Arkema has been participating in the AHRTI 9016 Material Compatibility Test Campaign, and we are continuing to participate that in future testing. That testing is still ongoing and is not completed yet, but we do have some preliminary results. Fluorine 516A is made up of 3 well-known components, as I mentioned previously. So we did not expect to see any material compatibility issues. And so far through the testing, that has been confirmed. We have not seen any major material compatibility issues with R516A, and we don't expect to see any of that testing concludes. Finally, let's look at the calculations for total equivalent warming impact, or TWE, comparing R134A, R516A, R513A, and R1234YS. Often, we simply look at GWP and assume the lower the GWP, the better it must be. While sometimes this does hold true, sometimes TWE analysis can help reveal a better picture of the total impact of the product. So we won't go into the full details of the TWE calculation. This is an industry standard calculation that is out there and can be reviewed and is available if anyone has any questions on that. But for this presentation, we will not go into the details of the actual formulas or the calculation of these numbers. What we will do is review the results. So we have 2 test conditions, both a standard ambient condition at 23 degrees Celsius, as well as a high ambient condition at 32 degrees Celsius. And what this is showing is that you have both the direct emissions from the product, which is from the GWP of the product, as well as the indirect emissions of the product and the performance of the product in a system. And when you combine both of these, you can see that R516A shows the lowest total equivalent warming impact of any of these products. The low GWP of R516A at 142 contributes to this. But in addition to that, the strong performance of R516A and its energy efficiency in a system also adds to that performance and that lower total equivalent warming impact. And this is where we see the biggest gain on the 1234YF. So that energy savings really helps push 516A past 1234YF. In conclusion, 4A and 516A is the ideal low GWP solution to R134A. As we've shown, properties of R516A very closely match R134A while having a 90% lower GWP. In addition, it has very strong performance in actual system testing in many applications. We've evaluated R516A in refrigeration, heat pump, and chiller applications, but it can be used in most any application that currently uses R134A, not just limited to those applications. In all applications, it will offer performance that is at least very comparable to R134A and potentially more efficient in many of those applications. And through further system optimization, more energy efficiency could be gained. It also has proved to offer more energy efficiency over other low GWP HFO alternatives, such as R1234YF. So having good material compatibility, a very low total equivalent warming impact, and being design compatible with R134A systems, R516A offers manufacturers the opportunity to make very few design changes when they're redesigning systems and allows them to adopt a very low GWP refrigerant with very little effort. I would like to thank everyone for their time and attendance today. To request more information about 4A and 516A refrigerant or ask any questions about today's presentation, please feel free to reach out to myself at the email address on your screen or through our account manager in Mexico, Javier Perez. Thanks and have a wonderful day.